Okay, so today we're going to start talking about the beginning makings of a proof. And we'll start with some algebraic proofs that you've already seen. You saw back in Algebra 1. And we'll bring those back and talk a little bit about how that helps us in our geometric proofs. Right? So the idea behind a proof is to make an argument. Right? We're going to be given some information and we want to go down and prove something else. And we'll do that through a series of statements. And so this is kind of where our deductive reasoning comes in, our conditional statements, understanding that if we have this piece of information, then that tells us something else. And so we can make those connections. Instead of just doing it through one statement, we'll do it through a string of statements to try to get down to something that we want to prove. And so, again, we're trying to build an argument. Every time we write a conclusion or write a statement, we want to back that up with some support, some evidence. Arguments are always better, always stronger when you can support your thoughts and support your statements, right? And so that's what we're going to do. In the algebra world, in the algebraic world, the supports that we're going to use, the reasons that we're going to use for the things that we do, are all basically the same. They're all properties. They're all properties of numbers. But it's these properties that allow us to do what we do to solve an equation, right? There are properties that if we use these properties, we don't change the solution to an equation. We just change what the equation looks like, right? For instance, the addition property says that if we add the same number to both sides of an equation, it doesn't change the solution to the equation. It just changes the way that it looks. The subtraction property says kind of the same thing, but the opposite. If we subtract the same number from both sides of an equation, then it doesn't change the solution to that equation. It just changes the way it looks. Multiplication property says that if we multiply the same number to both sides of an equation, then it doesn't change the equation, it just changes the way it looks. And these are the things that we've done to solve equations, right? We add numbers to both sides, we subtract things from both sides, we multiply things to both sides, and we divide things into both sides. The division property of numbers says that if you have two numbers that are equal and you divide them both by the exact same number, then you're still going to get two numbers that are equal. It doesn't change the solution, it just changes the way the equation looks. Now, the only caveat to the division property is that you can't be dividing by zero. But other than that, you can divide by anything you want. The substitution property is very useful both in algebra and in geometry. The substitution property which says that if A equals B, if two things equal each other, then you can substitute one for the other anywhere you want, right? So if A equals B, then you can substitute A in for any B that you want. Or the other way, you can substitute any B in for any A that you want, right? We can just replace each other with them. And then the last piece that we usually use to help solve equations is just the idea of the distributive property, right? Where if we have a number sitting or anything sitting outside of the parentheses, we can distribute it and multiply that into both terms inside the parentheses. That still doesn't change the solution of the equation, it just changes the way it looks. Okay? All right. So it's these properties, and it's just a series of properties that are named for whatever it is that we're doing that we use as reasons for our proofs in algebra. And the type of proofs that we use are called two-column proofs. Now, they're two-column proofs, not three-column proofs. And so I've taken out this middle column because we really don't need it, right? We're just going to talk about how to write our reasons and not worry about it. The reasons are, again, the support for being able to do what we want to do to solve this equation. So on the left-hand side, you see there, all we're going to do is we're going to start with this equation and we're going to solve it like we would any other time in any other algebra class. On the right-hand side, we need to give a reason for everything that we do. We're solving this equation in excruciatingly painful detail. Every little thing in here we got to show, right? So we've been given this equation, so we always start. So we start our proof with the fact that this equation was given to us. So we'll write given in as the reason as for why we put that in the first box. And as a matter of fact, that's what we'll always do for proofs. We'll always start by the given information. So this equation was given. Now, in order to solve this, hopefully you're looking at this and saying, oh, we've got to distribute. So we're going to distribute this 3 and this 2. And when we do, we get this guy, which is the same equation. It has the same solution as the first one. It just looks different. But the reason why we get to do that is because the distributive property says we could. So that's the reason that we're going to give, right? Now, if you were solving this equation without doing a 2-column proof, hopefully you'd realize that you can go in here and combine like terms. And when you combine these like terms, you get down to this equation here. And since we're combining like terms, or basically simplifying the equation, we can just call this simplify. Okay? All right. Now we're looking at this equation. And so what would you want to do first to start to solve this thing? Well, hopefully you're realizing that you want to collect your x's. So we're going to add 5x to both sides. That's possible. That's allowed. There's a property that says that we can do that and not change the equation, but just change the way it looks. And that property is the addition property. So that's what we give for our reason. Okay? And then we're going to actually combine these terms. Combine our like terms to get this equation. So we're going to simplify to get that. Okay? Now that you have this equation, I imagine it makes sense to you that we're going to subtract 12 from both sides. The subtraction property is what allows us to do that. So that's the reason that we give for being able to make that statement. And when we simplify, or when we combine our like terms, we get that next guy, which is 15x equals 30. Right? And with 15x equals 30, we divide both sides by 15 to continue to solve. And it's the division property that allows us to do that. Okay? And then when we actually divide out the 15 and then divide out the 30 by 15 and get x equals 2, that's us simplifying again. Okay? So that's pretty much it. I mean, we're going to solve the equation on the left-hand side, and the reasons that we're going to give are pretty much whatever we're doing in the next step. Right? So take that and try this one. Right? You've been given this equation. You want to solve it. We went ahead and put that in the first line and told you it was given. And then, by the way, for a little while anyway, we're going to give you the exact same number of lines that you need in order to finish out this proof. So if you don't use them all, or if you start to use too many, then that means you've gone wrong somewhere. You've either left out a step or you've included one that you didn't need. And so we'd want to take a look at that. Okay? But there's your equation. Do your steps and provide your support over to the right. Okay, go ahead and stop the video and then start it back up, and you can check your proof to make sure that it's the way that it should be. Okay? So, what did you do first? Distribute the 3, right? And you get 14x plus 21 minus 3x equals negative 1. And we can do that because of the distributive property. Right? Then we're going to combine these like terms and get 11x plus 21 equals negative 1. And that's just us simplifying the equation. Okay, to solve this equation next, we would subtract 21 from both sides. And the subtraction property says that we can do that and not change the equation or the solution to the equation. Now, we would combine those like terms here and here. That will give you 0. This will give you negative 22. And that's us, again, simplifying the equation. Then to finish solving, we're going to divide both sides by 11. And that's from the division property. Right? And then when we actually divide it out, or combine or simplify, which is what we're going to use for our reason, we will have our equation solved. And there you go. X is equal to -2. All right? That's an algebraic proof. And they're pretty straightforward because we only have properties to worry about. Properties for our reasons. And the properties happen to be named the same as what we're doing to the equation. Now, when it comes to geometric proofs, it becomes a little bit tougher to come up with statements because we have a slew of things that we can use for reasons. We have definitions, we have properties, we have postulates and corollaries and theorems and all kinds of rules. Okay? We will build those list of rules as we go through the class, and knowing that any of those that we come across we can use in a proof. Okay? All right, so some more properties that we can use. The reflexive property, and these are going to start to apply to geometric figures as much as just real numbers, right? So we'll show the reflexive property for real numbers, but then we'll also show what it would look like for segments and angles. And right now we're just worried about the lengths of segments and the measure of angles, so those numerical properties, okay? The reflexive property is the one that says that something's equal to itself. So a number is equal to itself, or A equals A, which is pretty obvious, and a lot of these properties are. But if you want to apply that to segment lengths, then segment AB, the length of segment AB is going to be equal to the length of segment AB. And this seems kind of silly to talk about, like the measure of angle A equaling the measure of angle A, but there are times where we want to use that reflexive property. Okay? The symmetric property. The symmetric property is what says that you can write an equality either way you want. So A equals B or B equals A. Right? Which is pretty obvious too, right? If the length of AB equals the length of CD, then the length of CD is going to equal the length of AB. But any of you computer programmers will understand that the way that you write that can make a big difference. Right? So we can switch those orders around and we know that it means the same thing. And same thing with angle measures. The measure of angle A equals the measure of angle B, then the measure of angle B equals the measure of angle A. Okay? The transitive property. The transitive property looks a little bit like law of syllogism from last time, right? The transitive property says that if A equals B, if those two numbers are equal to each other, and then B equals C, then we can jump straight from that and say that A equals C. Which is a lot like the transitive property, right? Because these guys are the same. Or sorry, the transitive, like the law of syllogism, because those guys are the same. And we can do that for segment lengths also. If the length of AB is equal to the length of CD, and the length of CD is equal to the length of EF, then we can jump over and say that AB is equal to EF, and we can do the same thing for angles. Right? If the measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then the measure of angle A equals the measure of angle C. Right? We can just jump right over and say that. Okay, these are all properties now that we can use as well. Okay? All right. So, your first geometric proof, okay, is going to be structured kind of like this. And again, we'll be given some information, like right here. And in this particular case, the given is going to come from the picture. And then then you'll have a proof statement. I want to prove CF is equal to AD. So we've been given that AB and EF are congruent and BC and DE are congruent, therefore their lengths are equal. And so how in the world does that get us to say that CF and AD are the same, right? That's a good question. But that's the nature of a proof. You start with some given information and you try to prove something that seems very unrelated. All right? Okay, so like I said, the picture gives us some information already. The picture says that AB is going to be equal to EF. Eventually we can get there by saying that AB and EF are congruent, then the lengths are the equal. Right? Same thing for BC and DE. Right? So we can say that in our first two statements here, and those were both given to us. All right? Okay. So that's the case. That was given. That's the information that we have. Now, the hardest statement to write in a two-column proof, in particular in geometry, is the one right after the given, right? You don't know where to go. You have no idea what you should write, and you don't know what you can say to get you to where you want to go. Well, at least right now, the advice that I would give you is that you write whatever you can that you know makes sense and you can support with a reason, with a property, with a postulate, with a theorem, or whatever. Okay? Well, since our givens are all centered around these pieces, then maybe we should worry about those guys. And in this next statement, it's suggested to us that we bring out the segment addition postulate and say that AB plus BC is going to equal to AC, right? Which is what we're saying here. And again, that's from the segment addition postulate. Okay? Now, we can do the same thing over on this side and say that DE plus EF equals DF by the segment addition postulate. And that's your statement 4. So again, I have no idea if those two statements are going to help me get to where I want to go. But I know they're true, and so I write them down in hopes that I can use them. Well, we actually can't. And so the next statement, and so statements are going to come from a lot of different things. They're going to come from a diagram. They're going to come from some previous information. They're going to come from a collection of multiple pieces of information that we got before. And so you have to just kind of bring all that together. Okay? Well, in this equation right here, we've got DF equals DE plus EF. Well, up here, DE and EF equal other things. Remember substitution property? That means we can substitute AB and BC in for DE and EF. And as a matter of fact, that's what we've done to get DF equals BC plus AB, and that's by the substitution property. Okay? Now, because DF equals BC plus AB, and BC plus AB shows up right here, then we can go ahead and replace BC plus AB with AC. We're doing substitution again. Only now we're taking two things that are being added together and substituting it in with one thing, the AC. And that's by substitution. Okay? Now, we see here that we're adding CD to the left-hand side of this equation. If we do that, then we have to add the length of CD to the other side, right? So that means that we're looking to write AC plus CD over here. And we're adding the same thing to both sides of the equation. The CD is a length, right? And so the addition property allows us to do that. Okay? Now, we really need one more set of statements down here that has been left out, and we need to add those in. Okay? We're talking about DF plus CD. Well, if you look at DF plus CD, then those two will add together and give you CF. So we can actually do the segment addition postulate here and say that DF plus CD is equal to CF. Right? And since we're using AC and CD over here, we can say that AC plus CD is going to be equal to AD, right? AC plus CD is going to be equal to AD. And this was all by the segment addition postulate. And since I'm adding this in, I'm going to use the same reason and just write it down once. Okay? But if you look now, we've got right? DF plus CD is equaling AC plus CD over here. And so now these two sides are equaling each other. That means we can jump down and say that CF and AD are equal to each other. We're just going to use substitution. We're going to replace this with CF and this with AD. And so we can say now CF equals AD by the substitution property, and that just so happens to be what we wanted to prove. Okay? So that's how we got there. It's going to be tough. It's going to be a little bit weird, but we got to try to fight through this and just start writing statements that you know is true using pieces that you were given, and it'll eventually lead you to where you need to go. All right? So that's it. It's time for you to try some proofs on your own. Give them a shot. We'll talk about them next time. Your homework's out in Canvas.